Good morning, students. Well, yesterday we discussed series combination of capacitors. In that series combination, how to find equivalent capacitance and what is the distribution of potential across the capacitors, right? And today, another combination, parallel combination of capacitors, right? Let us see what is parallel combination. Three capacitors of their capacities C1, C2, C3 are given to us. We have to combine these capacitors in parallel, right? See, we know this is first plate and this is second plate of this capacitor. Like this, this is first plate of this second one, second plate of second one, first plate of third one, second plate of third one. See how I am combining. All the first plates are joined. Okay. In the same way, all the second plates are joined. All the first plates are connected to a common point. All the second plates are connected to a common point. Right? All these are connected. This type of combination, you call it as parallel combination. Okay? The combination of the capacitors where all the first plates are connected to one common point, all the second plates are connected to another common point. That combination is parallel combination. See in the diagram, they are parallel to each other. Okay? AB. And to the combination, a battery is connected. A cell of battery is connected. Right? So three capacitors of capacitances C1, C2, C3 are connected in parallel to the combination. A cell of potential V is connected. Then what happens? First thing, see here, this is connected to this common point. This negative terminal is connected to this common point. This is wire, means this is plus and this is minus. Between these 2 points, what is the potential? V. Here potential V. Here also potential difference V. Means what is the potential difference across this? V. This is a common point. Common points these are. So across this capacitor also potential V. Same common points. Same common points for this capacitor also. So here also potential is V. Because if you just close these two, this capacitor is connected to the battery. If I close this one and this one, how it appears? This capacitor is connected to the battery. If I close these two, this capacitor appears connected to the battery in parallel. Yesterday I told you, when they are in parallel, potential is same in parallel lines, right? So the potential across this capacitor, and this capacitor all are same because they are connected in parallel and to the battery. This is one of the important points. See here, potential same. How the capacities are different. From those two, we can find out the charges on those two capacitors, right? If I ask what is the charge on this capacitor, see here, this is Q1 charge on this capacitor, Q2 charge on this capacitor, Q3 charge on this capacitor. They are different. Why they are different? We say, but capacity is different here. So whatever the total charge comes to the circuit Q, when it comes to this point, it finds three parts. So it divides as Q1, Q2 and Q3, right? And again comes as Q, like this. This is charge division. So here potential same, charge divides. Come on. So what we have? C1, C2 and C3. Capacities of given capacitors. How they are connected? V. Potential of battery. Right. When capacitors connected in parallel, see, potential difference across each capacitor is same. Potential difference across each capacitor is same, V. That means V1 is equal to V2 is equal to V3 is equal to V, which is equal to potential of the battery. Then charge divides. Charge is different. Okay. Then what that charge is? Charge on first capacitor Q1. Charge on first capacitor Q1 I want. Q. I know the formula. Q is equal to C1V1, that is C2V. Charge on second capacitor Q2, C2V2. Sorry, C2V. Charge on third capacitor C3V3, C3V. Capacitances are different, potentials are same. So Q1 is equal to C1V, Q2 is equal to C2V, Q3 is equal to C3V. Right? Well, if you observe this, the total charge coming into the circuit is Q. It is dividing as Q1, Q2, Q3. Then what the question we get? What is the resultant capacity? Okay. Yesterday I told you what is resultant capacity. If this total combination acts like a single capacitor, total combination acts like a single capacitor. I call this capacitance as Cp because combination is parallel combination. Capacitance of this capacitor is Cp, which draws same charge as this combination is drawing. This combination is drawing a total charge Q. If it draws the charge Q from the same battery, right? This capacitance we call it as resultant capacity of this combination, right? If these three combinedly acting like a single capacitor, Cp, such that it draws same charge as the combination is drawing from the same battery. This Cp can be treated as equivalent capacity or resultant capacity of that combination. Okay, our aim is to find out the Cp. From this diagram, what we can write? If resultant capacity is Cp, resultant capacity or equivalent capacity is Cp. From the diagram, what you can write? Q is equal to Cp V. Here also potential applied is V only. So between the terminals, what is the potential difference applied? V Cp, right? See, from these, from the diagram, what we can write? From the circuit diagram, total charge Q, this total charge Q coming divided as Q1, Q2, Q3. Q is equal to Q1 plus Q2 plus Q3, right? What is Q here? CPV. See here Q1, Q2, Q3, C2V, C1V, C2V, C3V. What is common in those? V common. So CPV, C1 plus C2 plus C3 into V. V get cancelled. And what do you get? Cp is equal to C1 plus C2 plus C3. This is the resultant capacity in parallel combination, right? Very important question, even for boards. Entrance point of view, formulas are so important. Okay? Come on, note down. Completed? Well, what are the points to remember in parallel combination? In parallel combination, first point is what? Potential difference across the plates of each capacitor same. Potential difference across each capacitor same, right? In the problem, if they ask you, what is the ratio of potential difference? See, connected to a barrier potential V, here also V, here also V, here also V, potential difference. What is the ratio of V1 is to V2 is to V3? V is to V. 1 is to 1. First point. Second, what is the ratio of charges on capacitors? Ratio of charges on capacitors. Just now we derived. I want Q1 is to Q2 is to Q3. What is this? C1V is to C2V is to C3, right? Which is equal to C1 is to C2 is to C3, right? Chart divides. Well, third, what is the charge on each? If total charge is Q, what is the charge on each? You can find simply by using Q1. C1V, C1 is given to you, applied potential is given, then charge on first capacitor, C1V, C2V, C3V. Sometimes they give Q is the total charge. Q is the total charge in the circuit. Then you know C1, C2, C3. Potential is not given. V is not given. Only Q given. You are asked to find Q1, Q2, Q3, and you know C1, C2, C3. Once capacitor is given, they will give you the value of capacitance. Along with that, they give the total charge Q. They are asked what is Q1, Q2, and Q3. Q1, Q2, Q3 means how this Q divides. See here, Q divides in the ratio of C1, C2, C3. C1 is to C2 is to C3. Can't we find? So when they divide in the ratio total, dividing in this ratio means QC1 by C1 plus C2 plus C3. Once ratio is given, you want to divide the total charge Q in this ratio. So to get Q1, total into C1 by C1 plus C2 plus C3. Direct formula you can use. In the same way, second one, Q into C2 by C1 plus C2 plus C3. Q3, Q into C3 by C1 plus C2 plus C3. Like, when you can use this, whenever total charge and capacitances are given, finding the charge on each in this way. Well, fourth, what is the net capacity or resultant capacity? Cp. Just now we derived. This is just sum. C1 plus C2 plus C3 and so on. How many capacitors are connected in parallel? Just there is sum. Right? Well, come on, note down. Completed. Next. If N identical capacitors each of capacity C, N identical capacitors each of capacity C connected in parallel, what is the resultant? What is the meaning? Like, look here. Plate 1, plate 2, plate 1, plate 2, plate 1, plate 2, 1, 2, like. All first plates are connected to this common. All second plates are connected to this common terminal. This is also parallel combination. Is it not same as this? C1, C2, C3, C4, C5, C6. All are connected to the same common terminal. In this, capacity of each same. What is the resultant capacity? What is the resultant capacity there? You know the result formula for resultant capacity is what? C1 plus C2 plus C3 and so on. C plus C plus C and so on. And C and C. Right. So this is something about parallel combination of capacitors. See, if n identical capacitors, each of capacity C connected in parallel, this is the formula. If they connected in series, yesterday we did that. If they connected in series, like this, they connected in series like this. What is the resultant capacity? CS C by N. Yesterday we derived this. When they connect in series, CS is equal to C by N. When they connect in parallel, CP is equal to NC. Right? Which is greater? 2 points come from here. Which is greater? CS or CP? See, this is N times of C. This is C by N. So, CP is greater than CS. Right? In the exam, they ask a question. To get more capacity, to increase the resultant capacity, which combination is preferable? To increase capacity, which combination? To decrease, to get the less capacity, resultant capacity, which combination? Series. Right? Series combination is preferable. Well, and one more they ask. What is the ratio of CP and CD? Ratio of the CP and CS. If the identical capacitors are connected first in parallel, then in series, here is the resultant, here is the resultant. What is the ratio of that? CP by CS. CP, NC, CS, C by N. Right? So what is the resultant here? A result CP by CS. If this N goes up, CC get cancelled, it is equal to N square. So CP is equal to N square of CS. This is the result to remember. Right? So CP is greater than CS, we said. How many times? CP is equal to N square times of CS. When? At this condition. Identical capacitors are connected. Well, come on, note down. Completed? Entrance point of view. Remember this formula. Well, next. Two capacitors, 2 microfarad and 3 microfarad connected in, well, parallel. 2 microfarad and 3 microfarad connected in parallel. This combination is connected to a battery of potential 10 volt. This is the situation given. This is the situation given. Then, first question is, what is C resultant? Second question, what is total charge in the circuit? Second question. Third question, what is charge on first? What is charge on second? What is the ratio of potential? And what is the ratio of charge? This many questions are possible on the same. See, how these two are connected? They are connected in parallel. Once they are connected in parallel, what is the resultant? Parallel. Formula is what? C1 plus C2. Okay. C1 plus C2. 2 plus 3. 5 microfarad. Finish. Total charge coming in the circuit is Q. We know Q is equal to Cp into applied potential. In this combination acting like a single capacitor whose capacity is this. Then total charge in the circuit CPV. Cp is what? 5. We applied 10. 50. 5 micro. Ten power minus 6. So 5 into 10 power minus 5. Okay. That is charge is coulomb. 50 microcoulomb. 50 microcoulomb. Well, next question. What is Q1? C1V. Q2 C2V. Yes, sir. Q is equal to CV. Once I connect a cell, potential on this, as they are parallel, potential is same in each line. Important note point. So for this, what is the charge? In this, what is the charge? C1V. Here, C2V. Right? C1V. C1. 2. V. 10. 20 micro coulomb. 3 into 10 power minus 6 into 10. 30 micro coulomb. 20, 30. Total is 50. See, 50 is coming in Here it takes 20, here it takes 30. They divide in the ratio of their capacities 2 into 3. In another way, also you can do Q into C1 by C1 plus C2. Just now I told you. Check out, you get the same answer. Q1 is equal to total Q into C1 by C1 plus C2. You get the same 20 microcoulomb. You just check in that way also. What is the ratio of V1 and V2? Potential across this, potential difference across this. Parallel combination, potential is same. What is the ratio of charges? Ratio of charges are according to the ratio of their capacities. Yes or no? No points, now only we discussed. 2:3 ratio. If you want, you can check it. 20:30, 20:30, 2:3 ratio. Okay. So once a parallel combination is given to you, you need to remember these points. If you apply simply, you get the answer. Okay. Come on. Next. One more model. See here. 3 capacitors. C, C. Each capacity is C. C, C, C. They are connected like this. These two are in parallel and this combination is in series with this. What is the resultant capacity? That is the question. Come on. Directly you can answer. But the way to follow is, first combination of these two acts like a single capacitor. How these two are? CC. If CC, two capacitors connected in parallel, resultant is what? C1 plus C2. Two capacitors connected in series, parallel, C1 plus C2. So resultant of these two, I call it as 1, I call this as 2, then C12 is equal to C1 plus C2, that is C plus C, 2C. These two combination completed. Or if you want, you can take another point here, A, C. Between C and B, another capacitor is there. Another capacitor C. I write it here. Another combination A, B. Let us take D, this point, because C stands for capacity. I call this as C3. So first I find C12. C12. How the combination is? Parallel. So C1 plus C2. C plus C. 2C. So C12 is equal to 2C. I got. Now for this. This is equal to what? How these two are? Series. When capacitors are in series, then C123. C12 is in series with C3. C12 is in series with C3. Like this you can write if you want. Okay. So what is the formula you have? C12 into C3 by C12 plus C3. Yes or no? If two capacitors capacitors are in series. C1 C2 by C1 plus C2 is the formula. Yesterday we studied. So C12 C3 are in series. C12 into C3 by C12 plus C3. Then what is C12? 2C. C3 is what? C by C12 plus 2C. C3. Well, so what is the answer? 2 by 3C. Yes or no? That is the answer. Like if a combination is given, if you practice it more and more without doing all this, when these two are parallel, see, parallel, immediately this is 2C. 2C or series 2 by 3C. Directly you can write the answer without doing. Okay? Come on, note down. This is first step. This is second step. You get the answer. C123 combinedly becomes C123. One more model. Completed? Come on, tell me the resultant. How these two are parallel. When they are parallel, they add up. So what happens? It acts like a single capacitor. This is 1, this is 2, this is 3, this is 4. So C12, 8 plus 8, 16. Because these are parallel, directly I am writing. Here is one point. Let us say some D. Then these two are series. When two similar capacitors are in series, 2, C by 2. Yes or no? C1, C2 by C1 plus C2, you just check out. It becomes C by 2. That gives six. You can check out. For this combination, C1, C2 by C1 plus C2. For this combination, C1 plus C2. You get these answers. So now this combination is a single capacitor. This combination is a single capacitor. Okay. Now these two are in series. C 1, 2, 3, 4. Series, what is the formula? C12 into C34 by C12 plus C. Find the answer. That's it. Okay. Like tomorrow, we discuss some more interesting models on capacitor combinations. Basic, these are. Okay. We continue. in tomorrow's class.